Welcome everybody to our presentation. This is Business Math course. We're going to discuss in this presentation the extreme values of a function. We're going to discuss the relative extrema using the first derivative test and the second derivative test. And we will end our presentation discussing the absolute extrema of a continuous function on a closed interval. This is Magda Talib Al Hinai from Sultan Qaboos University, and I welcome you all. We start this slide discussing decreasing and increasing functions on an interval a, b. So suppose we have a function f of x, and let's draw the xy axis, and here is f of x. If we have a value x1 and x2, and then we calculate the corresponding f of x1 and f of x2, we say that this is a decreasing function if whenever we have x1 less than x2, we have f of x1 greater than f of x2. So here we write what we've just said. The function f is decreasing on an interval a, b. We have here the open interval a, b. If x1 is less than x2, then we have f of x1 is greater than f of x2. Now let's draw a tangent line here, and another tangent line here, and another tangent line, and so on and so on. Whenever we draw a tangent line on such a function, we always have this line slanting to the left, and this is a line whose slope is negative. Okay, so here we have f prime is always less than 0 for all x in the interval a, b. In such case, we say that f is decreasing. So this is the definition according to calculus and differentiation, that f prime of x is less than 0 for all x in an interval a, b. Then we say that the function is decreasing on a, b. In the same way, we describe the increasing function. Again, we draw the x, y axes, and here is f of x. Again, we take two values, x1, x2. We calculate the corresponding f of x1 and f of x2, and we compare f of x1 to f of x2. We say that this function is increasing because whenever we have x1 less than x2, we have f of x1, this height is less than f of x2, this height in front of us. So if we try the tangent trick, again, we draw tangent lines to the curve. This curve, whenever we draw a tangent line, we find this tangent line is having a positive slope. So we say that a function is increasing on an interval AB if for all x on this AB, in this AB, we have f prime, the first derivative, greater than 0. In such case, we say that the function is increasing. Let's see this example on increasing and decreasing functions on an interval a, b. So we are given a function f of x is equal to 2 over 3x cubed minus 18x, and we are asked to find the intervals on which the function is increasing or decreasing. Of course, we need to start with the first derivative and compare it to 0 and see wherever the function is the first derivative is positive, we call the function increasing on that interval, and wherever the first derivative is negative, we call the function decreasing on that interval. So we start our solution, putting down the first derivative of this function. Of course, we differentiate, so we get here 3x squared. So we cancel the 3 with the 3 we get from the differentiation. So here we can put 2x squared minus 18. Okay, the derivative of minus 18x is minus 18. And next we take a 2 common factor, getting 2 into x minus 3 multiplied by x plus 3. This is the first derivative simplified. And we are checking for x, which makes the first derivative 0. So the first derivative is 0 at, yes, whenever we have this bracket is equal to 0 or this bracket is equal to 0. So whenever we have, so the first derivative is 0 at x equals plus or minus 3. So we go to the real line, we put the -3 and the +3 on this real line, and we split this real line into three intervals. This interval from -infinity to -3, the second interval from -3 to 3, the third interval from 3 to infinity, and we start investigating the sign of the first derivative. Here we put the first derivative. It is 2 into the bracket x minus 3 multiplied by the bracket x plus 3, and we take any test value on this interval. So anything less than -3 can be -3.5, -4, -5, -500, whatever value you take, you just plug it in here. We care only for the sign. So what's -3, -4, -3? It's -7, -500, -3, still it's minus. So wherever you put a minus value less than -3, you get this bracket to be minus. And also when you substitute with the same value here, you get also a minus sign here. So here we have the 2 multiplied by minus sign and a minus sign. No matter what the value is, we care only for the signs. Minus times minus is plus. So on this interval, the first derivative is always having a positive value. So here we can write that f prime of x is greater than 0, telling us that on this interval the function is increasing, and we put an arrow like this one going upwards, telling us that the function is increasing on this interval. We do the same thing on this at the second interval between -3 and 3. We write the first derivative. We take any test value, value for x from -3 to 3, and we plug it in here. The easiest to be is 0. You can take anything else between -3 and 3, but I will take the 0. So 0 minus 3 is a minus, 0 plus 3 is a plus. So here we have minus times plus, which is a minus, telling us that the first derivative on this interval will be negative. Yes. So the function is decreasing on this interval. Finally, we come to the third interval from 3 to infinity, and we take a test point, anything greater than 3, and we plug it into the first derivative. So if you take 4, you will have 4 minus 3 positive, 4 plus 3 positive. If you take 400, 400 minus 3 is positive, 400 plus 3 is positive. We care only for the signs, we don't care for the value. So here I have positive times positive, the whole thing is positive, telling me that the first derivative is positive from 3 to infinity. So we write f prime of x is greater than 0, telling us that the function is increasing on the interval from 3 to infinity. So we write this, f of x is increasing on the either here or here, and the or sign we replace it by a union. So f of x is increasing on the interval from -infinity to -3, union the interval from 3 to infinity, and we write it like this. F of x is decreasing on the interval from -3 to 3. And I want to give you a remark that this value, these two values, we call them critical values, and we will discuss them in the coming. In this slide, we discuss the critical values for a function f of x. The value x equals c, we call it critical value for the function f of x if it belongs to the domain of the function f and it satisfies one of the following conditions. If it makes the first derivative 0, if f prime of c equals 0, then we call c critical value as long as it is in the domain of f. Also, if it makes f prime undefined, then also we call it critical value as long as it belongs to the domain of the function f. And we move to examples. Okay, everyone, together we see this example. We have f of x is equal to x plus 4 over x plus 1, and we will give you also the first derivative, which you can easily find. We give you f prime is equal to x plus 3 multiplied by x minus 1 all over x plus 1 all squared. And we're asking you to find the intervals on which the function is increasing or decreasing and the relative extrema of the given function. So first of all, we start finding the domain of this function. We see that this function is defined everywhere except at x equals -1, because -1 makes the denominator 0. So the domain is all real numbers except -1. Now we take f prime of x. What are the values of x which will make f prime 0, and what are the values of x which will make f prime undefined? In other words, we're trying to find the critical values for x. So the first thing we try to find the values of x which will make f prime 0. So here we can easily see that f prime being 0 comes from the numerator, so we either have x equals -3 or x equals +1. So as I said, the first value which will make the f prime 0 is -3, and the other one is 1. Also, we have f prime does not exist at, yes, when x is equal to -1. But we know that -1 is not in the domain of the function. Okay, so we don't call this as a critical value, even though we take it on the real line and we start studying the sign of the first derivative to the left and to the right of each of the values we found. -3 and 1 are critical values. -1 is not a critical value, and that's why we take the open circle here. And we start studying to the left and to the right of -3. What's the sign of f prime? So we put the f prime. We all agree that the denominator is positive because we have x plus 1 all squared. Anything squared is positive. So the difference in sign in f prime will be coming from the numerator. So I take any value less than -3, let's say -4. If I put -4 here, yes, I get a minus. If I put -4 here, I also get a minus. Minus times minus is positive over positive, so the whole thing is positive. So the first derivative is positive in the interval from -infinity to -3, telling us that the function is increasing in this interval. Next, we move to the interval between -3 and -1. So we put the first derivative. Again, I say the denominator is positive, and I take any value between -1 and -3. Let's say we take -2. I put -2 here, I get a positive. I put a -2 here, I get a negative. So I get plus times minus over plus. The whole thing is minus, telling us that f prime is negative on this interval between -3 and -1. When the first derivative is less than 0, we have the function decreasing. Now we move to this interval. We have f prime, again we write it, and the denominator, as we said, is positive. I take any value between -1 and 1. Let's take the 0. I plug in here 0. I get positive. I plug the 0 here. I get negative. So I have plus times minus over plus. So the whole thing is minus, telling us again that the first derivative is less than 0 in this interval. So in this interval, the function also is decreasing. So between -1 and 1, the function is decreasing. Now we move to the interval from 1 to infinity, and I take any value greater than 1 and substitute in the first derivative to check for the sign. I take, let's say, 10, 100, 2, anything. So 10 plus 3, 10 minus 1, plus over the denominator, which is also plus. So we have the whole thing positive, telling us that the first derivative in this interval is positive. And this means that the function is increasing on this interval. So now we found that the derivative, the function is increasing here and decreasing here. Now when it increases and then it decreases, then definitely it reached a maximum at this point. So it tells us that the function is having a relative maximum at f(x) equals -3. And what is the maximum value? Take the -3, go up to the original function and substitute by -3. You will get the f maximum here to be -5. We do the same thing here. We see that the function is decreasing and then increasing. So definitely it reached a minimum value here. So at 1, there is a relative minimum for the function. We calculate the minimum value for the function, taking the 1 and going up there again and plugging in 1 here, 1 here, 1 here, and you get f of 1 equals 3, which is the relative minimum. In this example, to find the relative minimum and the relative maximum, we used the first derivative test. Next, we move to the second derivative test. In the present slide, we're going to talk about the second derivative test for a function to find the relative extrema. If we have the first derivative of of x evaluated at x equals a equals 0, we have three cases for the second derivative of f at x equals a. The first case, if the value of the second derivative of the function f at a is less than 0. In such case, we say that at x equals a, there is a relative maximum for the function f. The second case, if the second derivative evaluated at a is greater than 0, then we say that the function f has a relative minimum at x equals a. And in the third case, when we have the f double prime or the second derivative evaluated at a equals 0, then we say that the second derivative test fails and we should try to find another test for that specific value of x equals a to find the relative extrema at that x equals a. Let's take an example. Given f of x equals 6x power 4 minus 8x cubed plus 1, we are asked to use the second derivative test to find the relative extrema of this function. We start our solution evaluating the f prime and putting it equal to 0 to find the values of x which will make the first derivative 0. So the first derivative of this function is 24x cubed minus 24x squared, and of course the derivative of 1 is 0. Now, this simplifies to or can be factored to 24x squared into x minus 1. Putting this equal to 0, we can say that either x equals 0 or x equals 1. Now, we try to find the second derivative of the f of x. So we have f double prime of x is equal to, I differentiate the first derivative, it's 72x squared minus 48x. At x equals 1, the function has a relative minimum. We substitute for each x by 1. We find that f double prime is greater than 0, then we are here. So f double prime of 1 is equal to 24, which is greater than 0. But what happens when x equals 0? When x equals 0, we have the second derivative test failing because we put 0 here and 0 here, we get f double prime of 0 equals to 0. So we need to use the first derivative test to solve this problem. Next, we take an example given the demand function p equals 80 minus q over 4, where q is varying from 0 to 80. And we are asked to find q at which the revenue is maximum and calculate the maximum revenue. So we start our solution taking into account that the revenue is equal to price times quantity. So we say R equals to P times Q. I multiply this P by Q, I get 80Q minus Q squared over 4. Next, I differentiate to find the R by the Q and I put a derivative equal to 0. What's the derivative of 80Q? It is 80. What's the derivative of Q squared? It is 2Q, and here is the 4 in the denominator appearing. This tells us that Q is equal to 40. Now we need to check if this Q gives a maximum or a minimum to the revenue. We go to the second derivative test. If we apply the second derivative, we get d2r by dq squared is equal to minus 2. Yes, because 80 over 4 is a constant. When you differentiate it, it is 0. Minus 2q over 4 gives us a minus value. So this is negative for all q. So q equals 40 is called an absolute maximum. Next, we find the maximum revenue. What's the maximum revenue? It's the revenue evaluated at Q, which gives us maximum revenue. So the revenue of Q equals 40. I take every Q in this equation and I put 40 for it. So R of 40 gives us the R maximum. I put 80 times 40 minus 40 squared over 4. This is 400. Now, let's take another example. Given the cost function, C of Q is equal to Q squared over 5 plus 3Q plus 500. Find the Q at which the average cost is minimum. We are given the total cost and we are asked to find Q which minimizes the average cost. Okay, we start our solution writing the relation between the average cost and the total cost. We say it is the total cost divided by Q. So we take this cost function and we divide it by q. Q squared over q is q, and here is the 5 in the denominator. 3q over q is 3. 500 divided by q is 500 over q. The following step, we should find the marginal average cost. We differentiate the average cost. So this gives us dc bar by dcq. What's the derivative of the first term? It is 1 over 5. What's the derivative of the second term? This one is 0. What's the derivative of the third term? It is minus 5 over q squared. Next, we put this equal to 0. But first we make a common denominator. We put this equal to 0 implies that either q is 50 or minus 50. The quantity cannot be negative, so we neglect or ignore the minus 50 or we reject it. We just take the q equals to plus 50. Next, we find the second derivative of the average cost. And the second derivative of the average cost, I differentiate this part. What's the derivative of 1 over 5? It is 0. And here's the derivative of minus 500 over q squared. It's 1000 over q cubed. We need to evaluate this second derivative at q equals 50 and check for its sign. Okay, when we evaluate it at 50 and then we cube the 50, we get something which is positive, tells us that at 50 quantity equals to 50 units, the average cost is minimum. Okay, so we get absolute minimum because it's the only value for Q. We call it absolute minimum. Then the minimum average cost, if you're interested to find the minimum average cost, go to the average cost function, which is here, and plug in the 50 in every term, and you get the minimum average cost. C bar minimum is 50 over 5 plus 3 plus 500 over 5. This is 23. These were the two examples. Move on. We take the absolute extrema on a closed interval. This here we have the extreme value theorem. It says that a continuous function attains both its maximum and minimum values on a closed interval. Let's see the graph here. We have the x-axis, the y-axis, and a curve of a function as we see in front of us, f of x. And we take a closed interval AB, and we have this function is attaining its maximum value up here and its minimum value down here on the closed interval AB. We have certain steps to find the absolute extrema of a continuous function on any closed interval AB. Step number 1, we find the critical values of the function f. Step number 2, we evaluate the function f at the endpoints of the closed interval, and we evaluate it also at the critical values which belong to this interval, the open interval AB. Step number 3, we try to search for the smallest and the largest values we found from step number 2. The maximum value is the greatest value in step 2, and the minimum value is the smallest value we found in step 2. We go ahead and take an example. Given f of x is equal to x squared minus 4x plus 5, we are asked to find the absolute extrema of f over the closed interval from 1 to 4. We start our solution differentiating this f of x. The derivative is quite simple. It's 2x minus 4. And then we put f prime of x equals to 0. This gives us the critical value x equals to 2. Yes, when we put this equal to 0, we get 2x equals 4, so x equals to 2. Step number 2, we evaluate f of 1, which is the endpoint, the first endpoint, and then we evaluate f of 4, which is the second endpoint, and we evaluate f of 2, which is f of critical value. And then we compare which is the smallest and which is the largest of these values to tell us which is the absolute minimum or absolute maximum. The absolute maximum is f of 4, yes, because this is the largest value of all. And the absolute minimum is f of 2 because this is the smallest value of all.